Hi everyone, thanks for joining in. My name is Animesh Trivedi, and today I'll be presenting Stratus, Clouds with Microarchitectural Resource Management. And this is a joint work with Kaveh Razavi from ETS Zürich. So once upon a time, life in cloud was simple. Various computing abstractions, such as virtual machines, were attached to simple high-level resources like CPU cores and DRAM. And as different tenants came to cloud providers asking for these resources, cloud providers will find machines to allocate these resources on. So for example, here, tenant blue and tenant green happens to share the same physical machine, and also same low-level microarchitectural resources as well. In this case, shared L3 cache. So what could possibly go wrong here when the two tenants share the L3 cache? Well, this unsupervised or unintended sharing of microarchitectural resources have significant performance implications. A recent work from Eurosys 2018, Dcache has shown that by carefully managing the L3 cache in presence of a noisy neighbor, an application, in this case, Redis, can improve its performance up to by 60%. Not only just the performance, this unsupervised sharing also has significant security implications. Work from VU Amsterdam this year has demonstrated that an attacker, by carefully measuring the network round trip time, which is being serviced by a remote L3 cache, can detect activity of another tenant over the network. So are these two examples that I have shown you, are they L3 cache specific? The answer is no. Over the last couple of years, we have seen a new class of devices, computing or storage, enter mainstream computing. So we have now SmartNIC, non-volatile storage, GPUs, in-network switches, TPUs, FPGAs, and many more. And all these resources also bring their associated microarchitectural resources into the computing. And consequently, these diverse microarchitectural resources are here to stay. We make a case that these resources have significant security and performance ramifications. And the root cause of this is unsupervised sharing and consequently thereof lack of isolation. So the key problem that we are trying to tackle in this work is that how to manage microarchitectural resources in a principled manner. Our solution is a Stratus, a cloud with principled microarchitectural resource management. And the key property that we are after is isolation. So what is Stratus? Well, Stratus is a cloud resource allocation framework. In this work, we realized that all the security and performance requirements that we have are the two sides of the isolation. So Stratus is designed from scratch to capture and reason about microarchitectural resource isolation in a principled manner. So we see three key challenges in building Stratus. One is how to capture isolation, how to reason about isolation, and how to charge for isolation. Let's start with the first one, how to capture isolation. So to capture isolation in Stratus, we propose a declarative constraint interface. Isolation is captured as a constraint on microarchitectural resource allocation. So here's the syntax. So we have an isolate function, which takes three parameters: resource, scale, and quantity. Resource is your typical microarchitectural resources. We have identified that these resources can be of two different types, hard and soft. Hard resources are the one which have a discrete allocation units, like LLC cache lines or ALU or TLB slots. And the soft resources are the one which are typically contended in time. They are soft as in like a DRAM bandwidth or network bandwidth. Second, we have a scale. A scale is the extent of isolation request. It's a floating point quantity between 0 and 1. So naturally, hard resources can only take a quantity of 1. They are completely isolated in space. And the soft microarchitectural resources, such as DRAM bandwidth, can take a value between 0 and 1. And lastly, we have quantity. It's a number of resources for which this constraint must be satisfied. So it could be the case that the tenant is only interested in first 64 allocation of a cache line, or first 5 allocation of a on-chip on network card resources, caches, or TLB as well. So we can capture that here. Multiple of these constraints can be put together by the syntax of attach. All these constraints which were previously allocated, they have associated handle with them. And once these multiple constraints have been attached together, they can be passed during the allocation of resources to Stratus. So for example, to mitigate the netcat attack that I have shown you previously, we must isolate the LLC resources and the on-chip resources between two tenants. So that can be captured here by the constraint 1, which isolate LLC. It takes a value 1.0 because it's a discrete hard allocation, and perhaps first 64 lines of LLC caches. Second constraint, which is H2, takes all the NIC level resources, which is marked by star, and isolates them. We attach these two constraints and pass that to Stratus when allocating small virtual machines. Now moving on to the second challenge, how to reason about isolation. Well, the key challenge here is that there is no centralized entity or centralized place where all the relevant information is available at the one time. So to tackle this, we propose to build a cloud knowledge base. A cloud knowledge base is sort of a logically centralized database where we plan to put various information and knowledge such as topology, number of resources available, types, various information for the data sheets, as well as online measurements for utilization and occupancy that change during an operation of a cloud. So conceptually, cloud knowledge base is similar in spirit as a system knowledge base, which is found in the Barrelfish operating system. This is a structural representation of knowledge in one place, and it can be queried while doing the resource allocation for a tenant constraint. So for example, if a tenant specific constraints come into the allocation, we can evaluate it here and come up with the allocation strategy on which machines, which resources must be allocated. Lastly, how to charge for isolation? Well, if we have a look at the isolation spectrum, on the one end of this spectrum, which is the red side, we have low isolation, which typically yields high utilization because the cloud provider can pack multiple virtual machines, containers, or function on the same physical machine. It will lead to better efficiency. However, at the cost of perhaps low performance or security guarantees. On the other extreme of this spectrum, we have a very high isolation, which will result in the low interference between the different tenants and with a better performance and security guarantees. However, by trading off utilization of the infrastructure. So there's an inherent trade-off on this spectrum. And to capture that inherent trade-off, we propose the notion of isolation credit. Isolation credit is a currency that a provider can charge a tenant to satisfy their constraints. So this encourages tenants to specify only the relevant constraints to the provider, not just isolate everything under the sun for us. On the other hand, it also encourages provider to innovate better in isolation mechanism. Consider two cloud providers where one can charge less isolation credit to satisfy the same constraint for a tenant on two different infrastructures. So naturally, a tenant would be encouraged or would consider moving to a second cloud, which will charge less. And this notion of isolation currency can also be used as a one-dimensional quantity to explore the design space here. So for example, we envision Stratus could have two types of tenants. For example, one who knows. So these tenants are the one who knows which specific microarchitectural resources are critical for the performance and security requirement for them. So they can specify these constraints very specifically to Stratus, and Stratus would come back that, hey, to satisfy these constraints, we will charge you, let's say, 42 credits. On the other hand, we could have a tenant with just a budget, right? And this tenant can specify to the cloud that, hey, I have a budget of 42 credits. Give me your best constraint that you can satisfy to deliver the best security and the best performance under this budget. And in this case, Stratus would be able to explore the design space of constraints under a given budget and come back to the tenant saying that, hey, we can satisfy these kind of requirements. And tenants are then free to choose or reject the proposal from the cloud. So to summarize, in this work, we have presented Stratus, which is managing its microarchitectural resources in a principled manner. There are three key ideas in Stratus. First, we propose a declarative interface to capture the isolation requirement from the tenant in a systematic and a principled manner. Second, we propose a cloud knowledge base, a logically centralized database where we systematically will build all the information relevant to make informed resource allocation decision when allocating resource in the cloud under the specified constraint from the tenants. And lastly, to capture the inherent trade-off between a tenant and a provider for requesting more or less isolation, we propose a notion of isolation credit that a provider can charge to its tenant for satisfying its isolation requirements. We are just started to build Stratus. So naturally, there are multiple challenges and discussion points that we hope to get feedback from this workshop. First of all, we are exploring various mechanisms and policies which are available here today to build Stratus. So naturally, for certain kind of microarchitectural resources, such as LLC L3 caches, we have Intel cache allocation technology, Intel CAT, or we can use a various software mechanism like page coloring to ensure that there's no unintended cache thrashing between multiple tenants. But we yet have to explore systematically what other mechanisms are available for the variety of diverse microarchitectural resources beyond just the CPU. What are the different policies we should explore in order to make sure that the constraints are satisfied properly? Second big pillar is choosing the right constraints. It is non-trivial to figure out for what kind of workload, what microarchitectural resources are the most critical for the performance and security requirements. So here we envision a profile-guided exploration would be needed. And also we envision that perhaps not everyone wants to do their security analysis for their workloads. So a security expert will be able to provide security libraries with the predefined constraints that a tenant can download and use in Stratus. Lastly, there's the scalability of cloud knowledge base. Since we are in a process of building, it is yet to be seen that whether we can build a system that can scale to 100,000 or 10,000 machines. Can we do allocation under very strict time budgets of 1 to 10 milliseconds, which is typically required for, let's say, serverless allocations? And taking a step back for the discussion in this workshop, one can ask very fundamental question that is microarchitectural resources management is really worth it or not? We think it is, but we are very happy to see counter arguments, and we hope to have a discussion during the workshop with all the participants. We want to know that should we focus our efforts more on developing new mechanisms for microarchitecture or to do better policies, exploration of policy space? Can we have a better hardware support from the vendors, from the NIC vendors, non-volatile storage vendors, in-network computing vendors? And beyond that, we are interested in hearing what are we missing from the cloud operation point of view in building Stratus. So far, we have been focused on how to do efficient microarchitectural resource management and allocation, but we are aware that running a cloud is a complicated endeavor, and there are more than one concerns. And with that, I would like to conclude. Thank you very much for your attention and hope to talk to you all in the workshop.